Hello, welcome back student. Today we are going to see the algebraic laws and we will see the closure properties and we will see the decision properties and as well as we will see pumping lemma. Before that, uh, I gave you in the last class, I gave you the problem. So for that problem, this is a solution. I gave you this problem. So this is 2, okay, you can consider 2 or q, but considering q2. So this is a solution and already I have sent you the solution. The final regular expression is 0 closure 1 0 closure, okay. So here as you can see we completed the q1 and we completed the q2, but we have not used the q3. But whenever we get the result, okay, and when the final state, which one is the final state? Q2. So our final state, after using the final state, if we get the string, then we need to stop. We don't need to do this. If we did not get the string, that time we need to do all the state, okay. I hope you understand. This is one of the identity. So we will go today's class. Today we will see the application of regular expression. Basically regular expression are used in search tool, text file search in Unix, okay. The tool name is egrep. This command search for a text pattern in the file and list the file name containing the pattern. The pattern is very important, like how the pattern is there, a b b a, okay. What is a pattern that should be know in the regular expression, okay. So for that there is a using the egrep in Unix, okay. So the text pattern in the file and list the file name containing that pattern. So this is small application of regular expression. Now we will see the algebraic laws of regular expression. So already it is there and I am going to provide these notes also on my blog, okay. So this is algebraic laws for regular expression. First one is associative and cumulative. Second one is identities and annihilators. Third one distributive law, and fourth and fifth is idempotent law and law involving closure, okay. So first we will see whenever we have this m plus l plus m, then it will be m plus l, and if we have like this l plus m plus n, then you can take l plus mn, you can write like this also. So this is like already it is algebraic laws predefined. Whenever you need, whenever if required, you can use this, okay. This is cumulative law. First one, union of two language in either order are same, okay. If it is same, cumulative. The next one, this one is associative law for union. What we call this plus? We call this union, okay. We call this union. Lmn is equals to Lmn. This is, you can write dot or empty, then it will represent as concatenation. Lm does not equal to ml. Concatenation is not cumulative, okay. Whenever the cumulative is there, at that time m plus l, whenever the union is there, this will be cumulative law. When we are using the concatenation, that equation is not cumulative. When you have Lm, you have to write Lm only. Second one, identities and annihilators, okay. Phi plus L is equals to L plus phi is L. Whenever we get this kind of equations, any two, okay, you will get L, and phi is a identity for union, okay. Phi is identity of union. So this plus is nothing but union. epsilon L is equals to L epsilon is L. So what is epsilon? Identity for concatenation. Okay, phi L and is equals to L phi is the an annihilate annihilator, okay, for concentration. Annihilator. Third one, distributive law. L of m plus n is equals to Lm plus Ln. This is distributive. When like we are opening the bracket, m plus n L is equals to ml plus nl. Plus is nothing but union. Okay. Fourth one is the idempotent law. This already we have done. L plus L is equals to L only. This already we have seen in the regular expression identities. Okay. Laws involving closure. L closure, whole closure is equals to L closure only. Whenever we have language closure, whole closure, you can write L closure. If we have phi closure, means empty closure, so that time you need to write epsilon. Epsilon closure is also a epsilon. L plus is equals to LL closure is equals to L closure L. Whenever we have like this equation, L plus means L plus LL plus LL plus LL. This is without epsilon. This is without epsilon. Whenever we have keen plus, we will say this keen plus, or we will say just plus, and this we can say keen closure, or we can say just closure star. So this is start from epsilon. So because of that, it is L star L. Next one, L closure is equals to L plus union epsilon. Whenever we have like this, so you can write L plus union epsilon. Why? Because whatever the answer of L plus, that will be available in L star, just only we need to add epsilon. Okay, L question mark is equals to epsilon plus L, that is union. So this is a phi law of algebraic law. Whenever we do any operation, that time we need this. So already we have solved some of the problems. In that we saw we use the identities. Okay. So next, property of regular expression. There is a two properties of regular expression. First one, closure property on regular language, and second one is decision property of regular language. We will see these two one by one. Closure property has some of the properties are there. Okay, and decision properties also have properties. Closure property has 8 and decision property has 6. So we will see one by one. So here in the closure property on regular expression are defined as a certain operation on regular language which are generated to produce regular language. Okay, we are generating to produce the regular language. Closure refer to some operation on a language resulting in a new language that is of same type as origin operator on that is regular. So regular language are close under following operation. Consider L and M are the regular language. Okay, already we have learned the clean closure and positive closure in the previous class. Just clean closure is, it will include the epsilon. So R is a regular expression. Whole language is L comma M R closure. R closure is a regular expression whose language is L. Okay, whose language is L. So here R is a regular expression whose language is L. M. R positive closure is a regular expression whose language is L plus. Okay, L positive closure, and here L keen closure. So this is a closure property on regular language, and we'll have some of the properties like union. First one, union, we are doing like we are using the plus. Already we have done this. Okay, union is nothing but if L1 and L2 is there, regular language, so you can make it L union L1 is a regular language. Concatenation, concatenation, if L1 and L2 are the regular language, so we will write L1 L1 L2, okay, without anything, or you can just write full stop dot between that. That will represent as concatenation. What is this star? If L is a regular language, then L closure is regular. Okay, so because if L is a regular, so we can like L closure means a like this, so on. So you can write. Okay, complement. If L is a regular language, then L dash, this dash is nothing but complement, is sigma closure minus L is regular. Okay, so let here the thing Q sigma delta Q0 F been some DFA for L. When construct a DFA, D from L dash, where D dash is Q sigma delta Q and Q minus F final. So dash is nothing but whatever the complements means, whatever the final state, you need to change the normal state, and whatever the normal state, you need to make it final. So that is complement. Fifth one, intersection. If L and L2 are regular, then L intersection L2 is also regular. Okay, this is De Morgan's law. In L1 are regular, L1, L2 are also regular. Union as well as concatenation. Okay, this is intersection closure property. Set difference. Set difference. L1, L2 are regular language, then L1, L2 is also regular. Means what it is telling, if L1, L2 are regular, then L dash means you can say that is set difference, or you can say minus. L1 minus L2 is also regular. L1 minus L2 is L1 intersection L2 dash. So here you can say L1, L2 are regular, yes. Then here you can say L2 dash is regular, as well as you can say L1 intersection L2 is regular. So when this all are regular, so we can say L1, L2 is a regular. Okay. Reversal. What is this reversal? In the reversal, here it's taken the W, A1, A2, so on, AN, be a string the reverse W, AN, AN minus 1, AN minus 2, so on, A1, okay, reverse. It's from 1 to so on to N, and here from N to so on to A1. For a language, L subset of sigma closure, reverse L is W sigma, W epsilon sigma closure, that is associate with reverse W belongs to epsilon L. So here in this picture you can easily identify this is Q0 and this is some state, and here the final 1, final 2, final state 1, final state 2. This is D, that is DFA. Okay, if we take the reverse, so here Q0, it's going from here to here. So here is reverse. Here is going uh, from here to there, it's reverse. Okay, everything is reverse. So here we are using the epsilon to connect the final. So here q0 dash, when its epsilon is going to final state 2, when q naught dash on epsilon is going to f1. So what is the definition of NFA? D dash is equals to q dash sigma delta dash q dash f dash. So when we will take this d dash, so we will get this tuples. Okay, q dash, what is q dash? Q union q dash, q not dash. So whatever the q is there, we need to union with dash. Delta q comma a, delta q comma a is r subset r associated with delta r comma a is equals to q. Okay, so whenever we have q comma a, means is q on a, where it is going, it can go to r, or r comma a is equals to q, whatever the q. Next state, delta dash q not dash epsilon is final state. How we can say the final? Because here in the dash that is not connected, based on the epsilon only we are getting the final state. What is f dash? F dash is equals to q. So whatever the state is there, that is q. So then LD dash equal to reverse of L. Like this is a L and this is reverse of L. If you take the D dash, then LD dash is equals to reverse L. Okay, so this is about reversal. Next, homomorphic is one of the property of closure. Okay, one of the property of closure. Let sigma be two alphabets. Okay, so here we will may not be distinct. Their function h epsilon, this star is called homomorphic. Let w be a string, w is a string, and epsilon sigma closure, and w is a1 a2 so on an, then h of w is h of a1 h of a2 so on h of an. So L subset of sigma closure is h of L, whatever the language, that is h of w. What is w? a1 a2 a3 so on, is belongs to this star closure associated with w belongs to L. So if L is regular, then HL is also regular. Whenever the L is regular, definitely H of L is also regular. Take an example of a comma b, and this is another is b comma c comma d. So this is a 2 sigma and one this option. Define H by H of A is equals to DBCC. H of B is equals to BDC. Okay, this is H of A. If L is a regular language denoted by R is equals to A plus B closure or AA closure, so at that time, then R1 DBCC, okay, here what is A? DBCC plus BDCA. What is B? BDCA closure. In place of this we are substituting, and this is, you can take anything, but here just for example I am showing this. So here in place of A is this, in place of B is this closure. Then after that, what is A? A is DBCC closure denoted the regular language H of H of L. Okay, ninth one is inverse homomorphism. Let H of sigma is homomorphism symbol star is a homomorphism, and L subset of homomorphism closure define H inverse of language is W belongs to sigma closure associated with H of W belongs to L. If L is regular, then H inverse of L is also regular. So here homomorphism is nothing but if L is regular, then H of L is regular. In inverse, if L is regular, then H inverse of L is also regular. This is about the closure property. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 6 closure property. In the exam, maybe it will tell you to write the closure property, so you need to write this. Okay, the next topic is decision property. What is this decision property? Decision property is a decision property for a class of language is an algorithm that takes a formal description of a language. Formal description of a language, example DFA, and tells whether or not some properties holds. So example is language LMT, that time the decision property. And why we need to use this decision property? When we talk about protocol represented as a DFA, we noted that important property of good protocol were related to the language of the DFA. So here very good protocol were related to the language of the DFA. Second one, example, does the protocol terminate? Is the language finite? Okay, when you ask the question, it's taking the decision. Does the protocol terminate? It is asking, is the language finite? If finite, then it will complete. Can the protocol fail? Is the language non-empty? When you ask the question, it will, based on the decision property, it will give you the answer. So let's see the properties. What are the properties? So first we might want a smallest representation for a language, example a minimum state DFA or a shortest regular expression. So like this minimization, I think you remember that minimization of DFA. If you did not know, just go to the previous video and see the minimization of DFA. So in that we are taking the decision and we are solving the problem. If you cannot decide are these two languages the same, that is do two DFAs define the same language, you cannot find a smallest. You cannot find a smallest. If both are completing in the 4 state and it is also completing in the 4 state, so we cannot find the smallest one. If anyone is doing in the 5 state, if you are doing in the 4 state, solving the 4 state, then it is you can easily find the minimize. So this is 6 are there. Okay, emptiness, non-emptiness, finiteness, infiniteness, membership, equality. This is the decision properties of regular expression. We will combine this and we will see. Okay, this is 1, this is 2, and this is 3, and this is 4. So first we will see emptiness and non-emptiness. In the first is emptiness and non-emptiness. Step 1, select the state that cannot be reached from the initial state and delete them, remove unreachable. First step, if any state is there from the initial state, if it is not reaching the final state, delete them. Okay, if here final or any state which is not q0. Okay, it is not, so delete this. Step 2, if the resulting machine contain at least one final state, then the finite automata accept the non-empty language. If resulting machine contain at least one finite set, any final state, at least one, then finite automata accept the non-empty language. Third one, if the resulting machine is free for final state, then finite automata accept empty language. So what is this means? If final state we have, okay, if any final state we have at least one, then it will be accept the non-empty language. Non-empty language. What is in the third step? If the final state free, okay, resulting machine is free from final state, then at that time we will accept the empty language also. Fine. So this is a two, empty and non-empty. When we will accept the empty, when the free from final state means it is not defined any final state and no final state, at that time it will accept the empty language. When it will accept the non-empty language, at least one final state should be there. This is emptiness and non-emptiness. Okay. Third, fourth is finiteness and infiniteness. Third and fourth is finiteness and infiniteness. Select the state that cannot be reached from initial state and delete them. Move reachable, unreachable state. Same step of empty and non-empty. Step 2. Select the state from which we cannot reach the final state and delete them. Remove dead state. What is dead state? If we have the dead state is nothing but from here it is connecting, okay, and here nothing, like from here it is going, but we need to find the final state. When you are getting, so this is called dead state. Okay, if the resulting machine contain loops or cycle, then the finite automata accept infinite loop. Like if we have the loop like this, then it will be cycle or loop, then it will be go in the infinite loop. If the resulting machine do not contain loop or cycle, then the finite automata accept infinite language. Does not contain loops or cycle, then the finite automata accept infinite language. So this is the 4 steps of finiteness and infiniteness. So sorry, here should be finite. Here should be finite language. Next one is, fifth one is membership. Membership is a property to verify an arbitrary string is accepted by a finite automation or not. That is, it is a member of the language or not. So we need to, with the help of membership property, we will verify the arbitrary string, okay, that is accepted by the automation or not. Let M is a final automata that accepts some string over an alphabet. Let W be any string defined over the alphabet. If there exists a transition path in M which start at initial state and end in any one of the final state, then the string W is a member of M, otherwise W is not a member. In the simple words, if you have the number of states, okay, and here from the initial state, if it is reaching to the final state, okay, if it is reaching the final state, then W is a member of M, member of M, okay, otherwise it will not. W is not a member. So this is about the membership. Membership is using for arbitrary string to verify the arbitrary string accepted by the finite automata. Okay. Last one in the decision property is equality. Two finite state automation M1 and M2 is said to be equal if and only if they accept the same language. Minimize the finite state automation with the minimal DFA will be unique. Okay, if both are equal, if and only if they accept the same language, then only we can say this is a equality. Okay, next topic is pumping lemma. In the pumping lemma for regular expression, this is one of the important. This will be used if you want to prove the regular language is whenever the regular normally pumping lemma is used for to find the language is regular or not, and most of the time regular pumping lemma will give not regular language. Okay, so what is the theorem? Let L be a regular language, then there exists a constant n which depend on L such that for each string w in L, w belongs to L such that w greater than or equal to n, then we can break w into three states. W is equals to x, y, z. Okay, you need to divide in three. So what is the first one? Length of the string, whenever it is defined, length of the y string greater than 0 or y does not belongs to epsilon. These two conditions. Next, when you concatenate xy, the size of the string should not greater than L. That should be less than or equal to n. For all k greater than 0, then string xy k z is also in L. This is very important, very important in the pumping lemma to find the language is regular or not. All are important. So this is the three string we can break. We can say rules. Okay, what is the application of pumping lemma? Pumping lemma is to be applied to show that certain language are not regular. It should never be used to show a language is regular. If L is regular, it satisfies pumping lemma. Okay, if L is regular, it satisfies pumping lemma. If L does not satisfy pumping lemma, it is not regular. So whatever the regular language is there, if it is not satisfying the pumping lemma based on this condition, okay, so that is regular language should be satisfied, then only we can say this is a pumping lemma. Pumping lemma will say it is regular. If L does not satisfy pumping lemma, it is non-regular. So this is application of pumping lemma. Next one, method to prove the language L is not regular. What is the method to prove L is not regular? Method to prove. So here at first we have to assume that L is regular. First point. So that pumping lemma should hold for L. Okay. Use the pumping lemma to obtain a contradiction. What is the contradiction? First, select W such that W greater than or equal to N. Okay, whatever the W should be greater than or equal to N. Second point, select Y such that Y, the length of the string Y should be greater than 1. There should not be epsilon and there should not be 0. such select x such that x y less than or equal to n, that should not be more than n. We are taken same thing from here. Okay, assign the remaining string to z, whatever the string if it is remaining, assign to z. Okay, select k such that the resulting string is not in L, hence L is not regular, hence L is not regular. Okay, so here pumping lemma theorem. Okay, and this note you will get it. So pumping lemma regular is like, as I told you, this is L does not belongs to epsilon, this we saw in the previous slide. Suppose L is a regular, so here all the things, suppose A1, A2, so on, AM, this is W, okay, where M greater than or equal to N, whatever the M you are taking here, that should be greater than or equal to N, and each AI is a input symbol. So what is the input symbol? 0, 1, 2, so on till n. Pumping lemma Pi is equals to delta is Q0, A1, A2, so on AI. So note that delta is a transition function of A and Q0 is a start state or initial state of A. That's mean pumping lemma like P0 is equals to Q0. Okay, so this is P0 is equals to Q0. By the pigeonhole principle, there is one principle, pigeonhole principle, it is not possible for the n plus 1 different PIs for I is equals to 0, 1, so on to be distinct, since there are only n different states. Thus, we can find two different integers I and j with 0 less than or equal to I less than j less than or equal to n, such that Pi is equals to Pj. Now we need to break W is equals to XYZ as follows. As we mentioned, pumping lemma we need to divide. So first is A1, A2, so on AI. Second one, Y is equals to AI plus 1, so on AJ. And here Z is equals to this. Z is equals to AJ plus 1, so on AM. So here starting from the P0 and x is equals to A1, A2, so on AI, and here in the self loop y is equals to AI plus 1, so on to AJ, z is equals to A of j plus 1, j plus 1, so on AM. So here x may be empty, y may be empty, however y cannot be empty since I less than j, okay, here with this that should not be a 0 or epsilon. If the automation receives the input x y to the power of k z, k should be greater than or equal to 0. We need to check whether it accept or not. So when k is equals to 0, automation goes from the start state q0 is equals to p0 to pi on input x. Whenever you are giving the input x, based on that it is from p0 to pi such that pi is equals to pj. It must go from pi to accept state on the input z. Okay, this is some rules. When we see some example, then you can easily identify. When greater than 0, automation A goes from Q0 to Pi on input X. Okay, then rules, C rules Pi to Pi, comma K time. on input y power k and then goes to the accepting state on input z. So thus for any k greater than or equal to 0, that is xy to the power of kz is also accept by a. Okay, that is xy to the power of kz belongs to L. So this is important. Now see example here. First I will show you the first example. So here in this, given n greater than 0, okay, n greater than 0. So first I am taking n. Choose w is equals to 0 power 1, 0 power n, 1 power n. Therefore w length is should be 2n greater than n. So now given a partition w is equals to xyz, where xy is less than or equal to n and y should be greater than 0. So here you can see 0 0 0 0 n number of time and 1 is n number of time and y should not be 0. So we have selected some of the code here, and here x, y and z we selected. Note that the string of x and y consisting of only 0. So here what it is telling, when you are going with the zeros, should be x and y should greater than n, greater than n. Okay, let y is equals to 0 t, so x is equals to 0 n minus t and z is equals to 1 power n. So when we solve this, choose k is equals to 0, then xy to the power of 0, k is 0 now. So xz, y power 0 is nothing. So xz 0 is equals to, what is xz? 0 to the power of n minus 1, 1n. What is x? And what is z? N power n does not belongs to L1. Why? Because our L1 is 0 power m and 1 power m greater than or equal to 0. What does it mean by this? Means if it is 5 zeros, so that must be 5 ones. Okay, 5 1. This should be equal 0 power m and this is 1 power m. But when we go with this equation 0 power n minus t, so whatever the n is there, based on that if we do the t, then it will be not equal. So what the answer we are getting? 0 power n minus t we are getting, and here we are getting n. So this should not be, they are not same, so this is not regular. Okay, so this is about pumping lemma, and this is some of the examples like a power n, b power n, c power 2 power n, means second, third and fourth. This is also the same thing, this is also the same thing, x y to the power of 2 z, same thing we need to apply. Then at the end it will define L2 is not regular. So remember, every time whenever we are using the pumping lemma, most of the time it will be not regular. Okay, here also it is same question, O power p, so n greater than 0, w is equals to 0 power r, where r is a prime greater than or equal to n. So this is about pumping lemma. Okay, so fine. So here the next is same thing, pumping lemma, giving n greater than 0. So where 0 is r, where r is a prime greater than n, Now give a partition x, y, z where y is equals to t, then t should be greater than 0 because y should not be equal to 0 or epsilon as per the pumping lemma. Choose k is equals to r plus 1. So if we add in this equation x, y, z concatenation y to the power of k minus 1, so 0 power r, 0 power t whole power k minus 1. So you can write, if the base here base are equal, power should be added. So we added the power. Now r plus k minus 1 t is equals to r plus rt. Therefore k is equals to r plus 1 is k minus 1 is equals to r, is sending here. If it is in plus, it's go to minus. So r is 1 plus t. Okay, as r is a prime number greater than n, so n greater than 0, so r is at least 2, and t greater than 1 as y greater than 0, so t plus 1 is at least 2. So r 1 plus t is a composite number. R plus t is a composite number. So x, y to the power of kz does not belongs to L3. L3 is not regular. Okay, so we have taken here 4 examples and 4 are not regular. Okay, if we have the closure like this also, we can take, if L4 is a regular, L1 is regular, then it is a contradiction. In the contradiction, L4 is not regular. Intersection L4. So based on this, we will solve the pumping lemma, and most of the time pumping lemma will going to use to find the language is regular or not. So this is about today's class, and thank you for listening. Thank you.